Hello and welcome to my presentation on how to measure solar radiation. Please allow me to introduce myself before we start. My name is Jörgen KONINGS. I work at Flux as a team leader in one of our research and development teams. My background is in applied physics. I studied at the Delft University of Technology and I've been working at Flux since 2010. So in the field of solar radiation sensors, I have been involved with the development of a lot of new products which we released over the last 10 years, which is our complete range of secondary standard or Class A pyranometers as our 20, 22, 25 and 30. And I've also worked on an update of our pyrheliometer line with the models DR15, DR20, DR30. Over the last few years I've worked on a lot of our calibration and test facilities, I think temperature response, directional response, calibration, and all kind of different specification tests. I've been involved in several different measurement campaigns, calibration events, but also field events comparisons. And over the last few years I've also been involved with the standardization of pyranometer measurements. For today, this presentation basically follows the logic of our YouTube movies on solar radiation. We have two published movies, how to measure solar radiation and what is a pyranometer and how does it work. This presentation is split into three parts. The first part will explain what solar radiation actually is. The second part is how to choose a solar radiation sensor. And in the third part, I will discuss how to properly use a solar radiation sensor. So let's start at the beginning. What is solar radiation? When we say solar radiation, we talk about the energy coming from the sun, and actually the energy flux. So if you take the sun, what we measure is the energy incident on a surface, and we measure per unit time. So that means a pyranometer measurement is in watts per square meter, or in physical units, joules per second per square meter. So the amount of energy in joules you get per second time in an area of 1 square meter. If you integrate that measurement over time, you get joules, an area, or you get kilowatt hours. So you can actually integrate that to get the complete energy on a certain surface, for example during a complete day. The energy coming from the sun is more than just the visible light, which you see. It also includes the UV radiation and infrared radiation. And all those quantities are also part of what we call solar radiation. So whenever you hear about solar radiation, very quickly people introduce the concepts of direct, global and diffuse radiation. And what they basically mean is they're separating the energy from the sun into different components. And the first component is what's called the direct normal irradiance, often abbreviated as DNI. And it's defined as all the energy that's coming in a straight beam directly from the sun itself. And alternatively, you also have the diffuse horizontal irradiance, often abbreviated DHI, which is all the energy which is scattered throughout the atmosphere. So if you're standing outside on a sunny day, you can see the sun in the sky, you can feel a lot of the energy coming directly from the sun, but there is also a lot of light and energy coming from all the other parts of the sky. Now, if you take a measurement on a surface of the Earth and you integrate all the parts, so both direct and diffuse, you get a quantity which is called global horizontal irradiance, or GHI, and it's simply all the solar radiation from the complete sky. So this means there's also a relation between these three quantities. Actually, global is the sum of the diffuse plus the direct beam normalized with the cosine of the angle of the sun in the sky. So if the sun is straight above, you get more radiation from the sun than if it's at a lower angle. Now, solar radiation sensors. We actually have two different solar radiation sensors. a pyranometer and a pyrheliometer. So first let me explain what a pyranometer actually is. You can recognize pyranometer by the fact that you always have these domes. And a pyranometer measures the solar radiation from the complete sky. We say a hemispherical field of view. So it means it's integrating over a complete half sphere. And in the pyranometer measurement, all solar energy is included. They are direct, diffuse and reflected. So pyranometers are used mostly nowadays to monitor the performance of big power plants, in PV power plants, solar energy plants. And originally they have also been used in weather stations, in meteorological networks. And there is many smaller applications where you would want to know the energy from the sun. Greenhouse control, building automation, studies of reflectors of materials, and also it's an important quantity for measuring the weathering of materials, so the outdoor durability. You expose a material to radiation from the sun and you see if it ages over time. Well, let's talk about the construction of a pyranometer. There are many different pyranometers out there, many different models, shapes, sizes, but some fundamental components are always the same. So the solar radiation from the complete sky is coming in and it's being transmitted by one or two domes, which are made of glass, or sometimes quartz or even sapphire. This dome shape makes sure that you actually let through the beams from all different sizes. If you have a flat window, you would actually start reflecting sunlight from low elevation angles. Now the solar radiation, which is transmitted through the glass, hits the black surface, the black coating, and the black coating absorbs this energy and turns it into heat. So the coating itself becomes hotter, and this heat will flow to the housing, the body of the pyranometer, which is often aluminium. So in between this coating and the body there is what's called a thermal detector, or a thermopile detector, and what you get is this flow of heat will generate a temperature difference over this detector, which is converted into a small voltage. And this voltage is then your signal. Okay, so that's the pyranometer. Let's do the second instrument, the pyrheliometer. Now a pyrheliometer, you can recognize this instrument in the sense that it is always a tube. And this measures the solar radiation directly from the sun. So this instrument measures only direct normal irradiance. And so you see it graphically here. There is a field of view with a half angle of about 2.5 degrees, which is simply a standard choice by the WMO, the World Meteorological Organization. What makes pyrheliometers sort of special is that they have to be pointed at the sun in order to work. So they are mounted on devices which are called solar trackers. And you'll see a few examples later. Now, why would you use a pyrheliometer? Simply, for many times with just a pyranometer you can get a good measurement of solar radiation, but if you want to push for more and more accuracy, you use the direct normal irradiance measurement as an extra measurement. So for very accurate solar energy assessment, or for very accurate PV monitoring, you see pyrheliometers used. And in the large, most accurate, high-end climate networks, people also employ pyrheliometers to very closely follow the trends in the solar energy over different decades. Very specific in situations where you have concentrated PV plants. So in plants where all the direct radiation hits mirrors, and these mirrors are used to concentrate the light at a single location. In those applications, pyrheliometers are also essential, because those plants actually operate only on direct radiation, not on global. Now the pyrheliometer construction, it looks different in shape and sizes. The fundamental measurement principles are the same as with the pyranometer. So again, the solar radiation reaches the instrument, but this time only from a 5-degree field of view angle. And in this tube there are apertures which define this field of view. Now the windows of the pyrheliometers are often quartz. They transmit this radiation, and there will be some coating. It's not visible in the pyrheliometer, but it's somewhere here. This coating will be hit by the transmitted radiation, and again the coating will absorb the radiation and convert it into heat, which will flow through a thermal detector towards the aluminium heatsink behind the detector. Again, the thermal detector, then the temperature difference that is established over this thermal detector is transferred into a small voltage. So very similar working principle. Okay, so I explained what solar radiation is, and I've told you which solar radiation sensors exist. Let's go to the second part, which is how to choose a solar radiation sensor. And the first thing to realize is there is not something like a very simple single solar radiation measurement. Actually, you can define different quantities in which you are interested, and I've listed the table here. So if you want to measure global horizontal irradiance, that's just the energy on a specific spot, use a pyranometer. If you want to know this on a tilted plane, so in an angle, also a pyranometer is used, but then in a tilted orientation. And you often in literature see the term plane of array, which is the irradiance on the plane of a panel which is tilted. So direct solar radiation is measured by a pyrheliometer on a solar tracker. But let's say you want to measure only the diffuse part. So you want to eliminate the direct part from your measurement. Now you have to take that pyranometer and shade it from direct sunlight. You can measure reflected solar radiation with a pyranometer by turning it upside down. If you have a measurement both of an instrument that measures the radiation coming in and the radiation reflected from the surface, you can calculate what's called albedo or reflectance. And sometimes these instruments are also combined with long-wave radiation measurements, which measure thermal energy to find the complete energy balance. And these instruments are called pyrgeometers. I will show you some of these different applications of solar radiation sensors in a bit more detail. So here's a picture of the same instrument, the same pyranometer being used in 3 different orientations. In that sense, it's a very flexible instrument. So the up-facing instrument is measuring global horizontal irradiance. The down-facing instrument is measuring the reflected irradiance. And this instrument here is tilted in the same angle as the panel. So it's going to give you the plane of array irradiance. And here is an example of how you can use a pyranometer to measure diffuse radiation. You see the pyranometer is on the solar tracker, and there is a shading disk which blocks direct sunlight from reaching the pyranometer measuring surface. And as the sun moves, this tracker will move, and also the shading disk will move, keeping this instrument continuously shaded. So when you have to choose a solar radiation sensor, you have to pick the instrument that matches the quantity you want to measure. Now, if you look at our portfolio, we have several different product lines, pyranometers, pyrheliometers. You can also find albedometers, which are simply 2 pyranometers combined in a single instrument to measure reflectance. We do offer the pyrgeometers to measure the long-wave radiation, which is thermal energy. And we offer instruments which are called the net radiometers, where we combine pyranometer and pyrgeometer measurements in a single instrument to give you the energy balance. Now I will focus mainly on the pyranometers and the pyrheliometers for this presentation. Okay, so if you know which instrument you need, the next thing you have to consider is classification. Pyranometers and pyrheliometers are subject to something that is called classification, which means that all instruments come with a certain class. For example, a pyranometer will be spectrally flat class A. And this term actually means something. It's described in these international standards. And in this sense, you don't have to consider all the specific details or every specification of a pyranometer if you have to choose one. You can simply start with the classification. If you get a spectrally flat class A, you get the most accurate instrument available. If you get a class B or one accuracy class lower, if you go for a spectrally flat class C pyranometer, you're again an accuracy class lower. So often, many times, you will be working with an application standard, a standard that tells you which class pyranometer to use. I'll show you an example of how this works in practice. So take, for example, standard IEC 61724, which is a standard from the Electrotechnical Committee on how you should monitor photovoltaic power plants. And they specifically state that if you have a very high accuracy system, like the one you would have in a utility scale installation, commercially viable, you require high accuracy PV monitoring system, and it basically tells you use a secondary standard thermopile pyranometer for this system. Or nowadays we would say a spectrally flat class A. Another example, the World Meteorological Organization, they have a guide on radiation sensors, where they also have a table with characteristic of operational pyranometers. And they also state, for example, that spectrally flat class B, they use the term good quality, pyranometers are acceptable for network operations. So often the standards and accuracy classes, they're really designed to help you choose the right pyranometer for your application. Okay, let's zoom in on the different pyranometer models we offer. I've selected the few main ones here. So we have three models, SR30, SR15 and SR05. And you see immediately the classifications of these instruments are different. So SR30 is our spectrally flat class A instrument, SR15B, SR05C. Now the SR30 instrument has what's called recirculating ventilation and heating technology, which greatly improves the measurement accuracy and the amount of valid data points of this instrument. And it also offers what we call remote diagnostics. So this instrument will not only give you the solar energy, it also gives you measurements of the tilt angle of the instrument, humidity inside the instrument, the speed of your ventilator. I will talk about how these things help you in a good measurement later. So the story to go with the pyranometers. Start with the SR30G1. It's the main model, the most accurate instrument out there. And it packs all the features you want inside a pyranometer. You also need no extra ventilators. If a lower accuracy is acceptable, for example in network operations, you can also use the SR15, which is the spectrally flat class B model, and that one is also available with different analog outputs. So standard millivolt outputs or 40-20 milliamp, for example. Now the SR05, which is the spectrally flat class C, the smaller pyranometer, that one is ideal for general solar radiation measurements, where you buy large quantity of sensors and spread them out. Now, if you really need a spectrally flat class A pyranometer and also need to work with an analog output, there is also still the SR20 model available. Let's switch to the pyrheliometers. There is also three models I want to show you. We have DR30, DR20 and DR15. Now the DR30 and the DR20 are both spectrally flat class A instruments. The difference between these two instruments is that the DR30 is fully digital. It communicates via the Modbus protocol over a 2-wire RS485 output, where the DR20 is the analog instrument with a traditional millivolt outputs. In that sense, the DR30 will offer you the remote diagnostics. It actually has the same tilt angle and internal humidity information that you will find in the SR30. And of course in the DR20 that information is missing. And now there is also the DR15, which is a spectrum flat class B model, slightly more affordable, also only with an analog output. The story with the pi heliometers is also in essence very simple. The DR30 D1 is the main pi heliometer model. It gives you the most accurate data, the most control over your instrument. If you need an analog alternative, go for the DR20. And in cases where a lower accuracy is acceptable, you can also choose to use the DR15. Now all these 3 pi heliometers feature what is called window heating, which means you can actually heat up the quartz window in front of the instrument, which prevent dew and ice and frost from forming on this instrument. And these instruments are designed in such a way that this heating does not affect the measurement accuracy. Important again, all these pi heliometers do require a solar tracker. Now when choosing an instrument, one concept that we talk about a lot is the concept of data availability. So if you're going to measure somewhere, ask yourself, do you expect snow, frost or dew? And in cases where these events occur, you want to choose a pyranometer with ventilation or heating. I think this is a very striking visual example. You have a lot of different models in a snowstorm, and you see here the SR30 model using this recirculating ventilation and heating technology is actually the only instrument which is still giving you valid measurements. Even in these situations where there is no direct sunlight, there is still solar radiation to be measured. So that's a very important aspect to consider. Now snow is very extreme, very visible, but dew is actually in many climates, many locations on the Earth, the biggest problem. And also very effectively countered by ventilation and heating. Okay, so I've told you about how to choose a solar radiation sensor. I talked about classifications. The final part of this presentation, I want to talk about how to use a solar radiation. Now once you have it, you have to make sure that you get good data. And the basic use of this instrument is actually very easy. It's very simple. You put the instrument out there, you get a reading, you have a very direct measurement of watts per square meter of solar energy. If you want to measure solar radiation accurately, it actually requires a lot of knowledge, a lot of skill, and great care. People have been measuring solar radiation for many years. This used to be a field of scientists, nowadays on large commercial scales as well. And there is a lot of very good literature available. Things I often recommend to people that are new to this field, the Baseline Surface Radiation Network Operations Manual, which is the premier climate measuring network. The National Renewable Energy Laboratory of the United States published a handbook for collection of solar resource data. The WMO, the World Meteorological Organization, have a guide to meteorological instruments, and there's many international standards that will actually give guidance on how to use these instruments. And I think that the picture is very clear that it's care. You have to take good care to get a good measurement. So when using a pyranometer, the first thing you start is location. Where will you place this instrument? Now realize that pyranometers see the complete sky. So in an ideal world, the entire area above the black sensor surface in a complete circle around the instrument is completely free of obstructions. Now that's often not achievable, but the least you can try to do is try not to block the direct beam at any day of the year. And there is many resources available online where you can chart the location of the sun in the sky of your specific location. And of course, reflective surfaces, you have to be very careful. So if the sun is reflecting from a surface, it may impact your measurement. And if you have strong lamps on your side, the pyranometers are also sensitive to energy from normal light sources. Now, when people integrate pyranometers in meteorological stations, for example, like this picture here, which offers measurements of temperature and relative humidity, that's why wind speed in this case as well, that's why you will always see the pyranometer on top of the instrument to make sure it's not interfered by with the other instrumentation. So once you've picked your location, you have to make sure that you mount your instrument, you install the instrument. Two main requirements. The pyranometer should remain fixed. It must not move, of course, and it should also remain level. The tilt of the sensor surface will impact your measurement. So it's very careful. You have to be very careful to install this instrument completely level and also check whether this level is actually maintained. Now if you turn the pyranometer upside down, there's two M5 threads for mounting this instrument from below, or there is a single M6 thread provided in the center. But recently many instruments now come with dedicated brackets and leveling mounts, which will make the mounting and the installation itself much easier, but also provide a much more fixed long-term solution. For example, this is a picture of an SR30 instrument using a PMF001 bracket to mount this instrument on a vertical pole, where you can actually control the angle and fix the sensor once it's level in the right tilt angle with a spring-loaded bolt. And here you see a picture of the SR05 with a tube mount ball leveling option fitted to it. So you can actually install this instrument on a horizontal tube, set it level with the visual bubble level, and then fix the sensor level with an hex key. And these are examples of solutions how you can actually properly install and maintain a long-term level of your instrument. Pyrheliometers also have to be mounted. Slightly different story because they are fitted on solar trackers. Now all the pyrheliometers in this world are standardized on 38mm tube diameters. And our pyrheliometers fit all the common solar tracker models. Well, if you have doubt or if you want to be sure, you can always contact Huxiflux to check the compatibility of the pyrheliometer with the solar tracker. You see some pictures of examples. So once you have this instrument installed, you have to of course make sure you get the data into your data acquisition system. So you have to look for data loggers. Pyranometers, traditionally analog instruments, small millivolt signals. Data log accuracy is actually critical to this measurement, especially if you want to get a good resolution and a good accuracy for low voltage, low flux levels. There are amplified voltage outputs available, which can relax these requirements on your data loggers a bit. So for example, a 4 to 20 milliamp or a 0 to 1 volt output. Well, this is an example of a data logger. There is also digital pyranometers on the market for the last few years, have very quickly become the popular go-to pyranometer model. And they have the benefit that they are directly input into your computer or into your SCADA system, which is a data acquisition system. This allows people to build large networks and integrate them into their bigger power plant systems, the monitoring systems. There is a lot of advantages when using digital pyranometers. You get all kind of information stored inside the instrument, you get temperature corrected data output, you get remote diagnostics. Whenever you install digital instruments of any kind, you have to pay attention to the grounding of your instruments. It's a very sensitive measuring instruments, often installed in situations where you have high currents. we have a lot of literature available, we have some recommendations in our manuals, and when in doubt, please ask us for instructions. Now finally, once you have your instruments installed, you have your data acquisition set up, you have to take care of your instruments. And that's often called the concept of maintenance. How do you maintain your pyranometer or your pyheliometer? The fundamental thing you have to do is to make sure that you keep your optics, your domes and your windows clean. Clean of dust, clean of water, and aside from that, you also have to check whether your instrument is still level and check the humidity inside your instrument. Now generally the recommendation is to do this basic maintenance schedule weekly. And in some applications in very accurate climate research networks, they actually require, for example, daily maintenance, where they have a scientist on site to every day take care of this instrument. Also, there is the concept of recalibration. Every 2 years, take your instrument out of the field, have it recalibrated to check whether the instrument itself is still stable. Now, pyheliometer technology is inherently very stable, but still recalibration is the best way, is a very strong way to spot errors with your instrument in the fields. Many applications now move to yearly recalibration. Now this is a very nice ideal picture. So let me go to the slide on maintenance in the real world. Maintenance is something that people very often very easy to miss. It's a very expensive thing to do. You have to pay people to maintain your instruments. And sometimes it can even be very difficult. Pyranometers are mounted in remote locations. This is a picture of a site in the US where they have a net radiometer installed on an arm, and after installation they see this arm, which is like 8 meters long, is actually, this instrument is slightly out of level. And also, how do you now start to clean this instrument? And even though standards now demand maintenance, which may force you to invest, it's important to realize that maintenance is critical for your measurement accuracy. So you have to be realistic in sensor selection. If you cannot afford, or if it's not possible to do proper maintenance, there is not much to be gained by getting a very accurate, expensive instrument. The accuracy you lose by the lack of maintenance easily offsets the performance specifications from one class to the other. Now the final point I want to talk about when we talk about how to use a pyranometer or a pyheliometer is the concept of quality control. So you have data coming in continuously, and the main recommendation I always give is check your data, see if it makes sense. This can be done automatically, may require some experience, but it's the fastest way to spot issues in the field. There is several methods available out there, different concepts. A few basic ones, you compare it with model data. You check with physically possible limits. Right, if you have a very strong negative signal, if it's higher than what's coming in from the from the atmosphere. And if you have multiple instruments, it's also very strong to compare the measurements of multiple instruments. I'll show you 2 examples of how quality control can help you. You see here a measurement of an SR20 and 2 SR30s, where the SR20 is the orange line, the SR30 is the purple line. And the purple SR30 is running what's called a low power mode, so the recirculating ventilation and heating technology is not used. And then you have a red line here, which is the SR30 in its standard mode, so where actually ventilation and heating are applied inside the instrument. And the green line is a model line. It's an estimate of GHI, which you would get from a very simple model for a clear sky. Now, without the green line, it can be very difficult to tell which sensors are right. You may even assume that these two are right because there's more of them. When in fact only the SO30 in standard mode is one measuring the right radiation measurement during early morning, and this is an effect of dew. So SO20 and SO30 in low power mode with no heating applied, dew forms on the instrument dome, and it actually acts as lenses focusing the light, so you get an overestimation of your solar radiation. Another example, the internal consistency. We talked about how the global measurement contains both the diffuse and the direct. Now, if you have a system set up where you measure all these three quantities together, as they often do in very accurate solar radiation stations or BSRN-like measurement networks, you can check these instruments for consistency. So these are examples of plots for different sites, different years, where on one axis they will plot the measured global, and on the other axis they will plot actually the direct times the cosine of the zenith angle plus the diffuse. And in an ideal world, this is a straight line with a slope similar to 1. So for example, this is an example of a very nice result. Here you see that there is some data which is obviously has some errors, and in this plot you see that there's a lot of messy data points, and then of course from here you would have to start studying what is causing these errors. Could be issues with any instrument, could be issues with your trackers. But if you have the components available, it is a very strong quality control method. Okay, to summarize this presentation, we covered three main subjects. First, I tried to explain what a solar radiation sensor is and what solar radiation itself is. We introduced the concepts of direct, diffuse and global irradiance. And I have explained what a pyranometer is and what a piheliometer is. In the second part of the presentation, we discussed how you can choose a solar radiation sensor. And it very often starts with the accuracy class. So ask yourself, does this application prescribe a certain accuracy class? This helps your selection. And I showed you the main specifications of the different instruments. And in the third part of this presentation, we spoke about how to use solar radiation, how to use it well. I discussed the importance of mounting and the tools available for properly mounting your instruments. We discussed maintenance, stressed the importance of maintenance and how hard and how expensive this can often be. And I've showed you some examples of how quality control on your data can greatly improve your measurement. So thank you very much for your attention.